Welcome to Making AIML Simple, Fast, and Cost-Effective with Google Kubernetes Engine. My name is Maulin Patel. I'm the product manager at Google Cloud. And I'm very pleased to introduce our distinguished colleague from BCG Digital, Mahadevan and Murali.
Thanks, Maulin. Hi, my name is Mahadevan. I'm a principal data scientist at BCG Digital. I'm a mechanical engineer and have a deep focus in working on system-level modeling and building analytics.
Hello, good afternoon. I know it's right after lunch, and a little nap makes it easy and nice. But it's Kubernetes, okay? It's exciting. Okay, let's get started. Anyway, I'm Murali. I'm a principal analytics advocate with BHE. My primary focus is on data and infrastructure. I work with the customers basically in moving the data to on-prem or cloud, wherever it is, and making it consumable, and then handing it off to the data scientists like Mahadevan to do their magic. Thank you.
Thank you, both of you. So let's get started. So today we are going to talk about two hot topics in the computer industry. First is artificial intelligence and machine learning, and second is Kubernetes. Both are critical pillars in today's modern computing environment. In today's digital economy, data is the currency. For many of us, data is the lifeblood of our company, and we want to convert data into meaningful information, actionable intelligence. AIML is the engine that helps us convert the data into actionable intelligence. And with the actionable intelligence, we can make better business decisions and drive actions in our organization. Industries all around the world are investing very heavily into AIML capabilities. At Google, our mission is to make AIML simple, fast, and cost-effective. We want to make AIML simple so everyone in your organization can benefit from it. We want to make AIML fast so you can build the model fast, train them fast, deploy them fast, and get insight faster. We also want to make AIML cost-effective in order to democratize AIML so that it's accessible to everyone. So when we think about AIML, we typically think about building models and training models. But in reality, AIML involves a lot more than building and training models. Typically, the ML code is a very small part of the end-to-end AIML toolchain. We need to recognize that AIML is a team sport. A lot of skills are needed in order to build end-to-end AIML application. For example, a data engineer may gather the data and cleans the data. Another engineer may extract feature out of the data. A data scientist may build a model. An application engineer may convert the model into application APIs. And an end user may use the model built using those APIs. So anyone who has ever tried to build an AIML team knows that there is a shortage of AIML skills. So how can we make these scarce resources 10x more productive? How can we give them an environment that helps them innovate faster? That's why we have built cloud-native AIML platform. So world is moving towards cloud-native computing, and Kubernetes is the de facto standard for orchestrating containerized workload. We have brought the power of Kubernetes to the world of AIML. Kubernetes makes AIML workflows simple, composable, and scalable. With the help of Kubernetes Platform, a data scientist can train and deploy model without having to worry about underlying infrastructure. Simply choose your favorite ML framework, pack the model up into containers, and deploy them on Kubernetes at scale. Kubernetes will scale your models from a single node to the thousands of nodes depending on your compute requirement. It will make you more productive. And the best part is you will be able to reproduce results reliably across the platform. So let's think about why Kubernetes is an ideal platform for building AI/ML toolchain. So there are three core reasons why. First is portability. Kubernetes enables cloud-native open standardized API, which means you can seamlessly port your workload between cloud and laptop and your own private data center without having to change your source code. Number two, it makes your workload scalable. You can scale from a single node to thousands of nodes. Also, Kubernetes supports hardware accelerators such as GPUs and TPUs and provides you higher level abstractions like autoscaling or auto provisioning, which makes scaling your workload super simple and easy. And number three is productivity. With the help of Kubernetes, you can free up your users from managing their own workstations or VM. As a data scientist and data engineers, you can focus on your core mission, which is to basically build and deploy models without having to worry about underlying infrastructure. So if you are a data scientist, you are wondering, do I have to master the Kubernetes skill in order to benefit from all these features? Great news, you don't have to master those skills. Data scientists typically build their model inside the notebooks. They have their preferences for their libraries and machine learning frameworks. To make their work super simple and easy, we are providing hosted notebooks. And our hosted notebooks are pre-configured with one of the widely used libraries like Pandas and also many other machine learning frameworks like TensorFlow, Keras, and many, many more. All you have to do is open up your browser, connect to your data, and start building models inside your notebooks. The best part is you can train the model and deploy your model on the top of Kubernetes directly from your notebook. You don't even have to leave the notebook. So you get very notebook-friendly experience and all the benefits of Kubernetes. So what if you are an expert Kubernetes user? Great news. Kubernetes also provides you high-level abstraction that helps you run TensorFlow jobs very simply and easily. For example, you can make use of TF job. What the TF job does is it integrates TensorFlow distributed training and estimator APIs with Kubernetes. And it allows you to scale training and leverage the hardware accelerators which work with Kubernetes. So as a user, you can benefit from a very vibrant ecosystem of Kubernetes products that are out there when you work and develop your models on the top of Kubernetes. You can use Kubernetes dashboards for monitoring or Prometheus and Grafana and many, many other tools which community have developed over many years. So Kubernetes also makes TensorFlow serving super simple and easy. So let's say you build a very sophisticated movie recommendation engine. Now you want to test your model on a small scale with the global traffic. Now if you deploy your model in US, the traffic will be overwhelmingly from the audience which loves Hollywood movie. If you deploy this model in India, the traffic will be overwhelmingly from the audience which loves Bollywood movie. So you have a dilemma. On the one hand, you want to test your model through a global cross-section of the traffic. On the other hand, you don't want to deploy your model globally, because it's an experimental model and you are concerned about the blast radius of something going wrong. So what do? Here again, Kubernetes and Istio come to the rescue. With the help of Kubernetes and Istio, you can actually configure your load balancer so that your model gets a cross-section of the traffic from many, many different regions. So you can test the fidelity of your model across the regions without having to deploy your model globally. So what it means is Kubernetes helps you address many model rollout challenges. It makes model lifecycle management super simple and easy. So far, I talked about how Kubernetes simplify model building, but the biggest challenge is model training. We have seen time and time that building a complex model takes really, really long time, mainly because it takes very long time to train them. So in order to expedite the model training, we have brought the power of GPUs to the Kubernetes. So with the help of GPUs, you can turbocharge your compute-intensive applications. We support a wide range of GPUs in Google Kubernetes Engine, and they have a different cost versus performance profile, so you can choose the GPU that best suits your application needs and your budget. You can get started with the Kubernetes GPU K80, which we support, which gives you entry-level performance at the lower cost. But if you decide to turbocharge your application, you can use V100, which is very powerful GPU and allows you to expedite your model building and model training as well as model serving. And the best part is that GKE also supports preemptible GPU. So for your batch workload, you can reduce the cost by 50 to 70% by using preemptible GPUs. So we also offer you many more choices for hardware accelerators to accelerate your machine learning workload. So for example, on Google Cloud GKE, we also support Google design hardware accelerators, which we call Cloud TPU, which will further accelerate your AIML workload while reducing the cost. And I'm super pleased to announce that our third generation Cloud TPUs, version 3, are now generally available on Google Kubernetes Engine starting today. So you can access those very powerful cloud TPUs just like you will access CPUs and GPUs on GKE. You don't have to manage them on your own. Google Kubernetes Engine actually manages them for you. Also, the best part, they are available as a preemptible load, which means you can substantially reduce the cost of batch training by using preemptible cloud TPUs. Google Kubernetes Engine also supports cluster autoscaler with GPU and TPUs. So with the help of cluster autoscaler, you can automatically scale up and down the clusters for best performance over cost. So nodes with GPU and TPU get created when you need extra compute capacity. You don't have to manually schedule them. And the nodes with GPU and TPU get deleted when they are idle. So you get two core features: on-demand extra compute without you having to manually schedule them, and number two, freeing up the resources when they are not used, which means you don't have to pay for them. So it optimizes the cost and gives you like a supercomputing powers without manual work. Now let's look at a real-world example. What would be a better example than a software program that defeated world champions and professional Go players? This was a historical milestone in the history of artificial intelligence when a software program defeated world champions. So for those who are familiar with Go, Go is a strategy board game which was invented more than 2,500 years ago, and ever since it has captivated human mind. It is played on a 19 by 19 board, and players actually alternate placing the stones on an empty cross-section, and the player that surrounds more territory actually wins. So Go is an incredibly difficult program for a computer to learn, and here is why. Just imagine that the number of board configurations that are possible on a Go board are actually more than number of atoms in the universe. Number of atoms in the universe. So just a brute force approach does not work. Number two, for every move, you have too many choices available, and its impact is realized over a large horizon, which makes it very, very difficult for a computer to analyze through. And number three, unlike chess, which has like a rules when the game is over, for example, one player checkmates the other, Go has no rule where it dictates the termination of a game. Game is over when two parties agree, which means it's very difficult for a computer to analyze when the game is over, right? So AlphaGo Zero was the first program which defeated the professional Go player, and I'm going to talk about MiniGo, which is an open source independent implementation of the AlphaGo Zero. So let's see how Go algorithm is implemented. So MiniGo is actually implemented using reinforced learning algorithm. So in the reinforced learning, there are two critical steps. In the first step, the model plays against itself, which is called a self-play, and it records the search space for every move. In the second step, the data that is gathered in the first step is used to train the model and make the model better. Now, again, this better model plays against itself to create more data. And this more data is used to create even better model. So this loop keeps repeating, and model gets better and better and better. Now, remember, every Go game has hundreds of moves. And for every move, the model has to do inference for thousands of search spaces. So the amount of compute that is needed for inference actually dwarfs the amount of compute needed for training. So inference is the biggest bottleneck. You can see in this picture, self-play arrow is much bigger than the training arrow. It's on purpose. So how can we basically make sure that this game can be trained in a short amount of time? So the great news here is that all these games can be played independently in parallel because they are completely independent. So using that, we implemented the MiniGo on the top of GKE, Google Kubernetes Engine. And initial implementation used to take more than a couple of months to train. Now imagine you want to experiment with that. You start a training and then says, come back in 5 months when training will be over. That would be quite frustrating, isn't it? So with the help of cloud TPUs, we could scale down the training time on the top of Google Kubernetes Engine to just a couple of days. So after we fully trained it, the model used to play millions of games in every single day. Every second, 15 to 13 games can be played with this advanced feature. We could devote up to 150 petaflops of compute to a single problem very easily. So cloud TPUs are incredibly powerful machines. So this is a picture of cloud TPU version 2. And we used it to train a very well-known model, which is RasNet 50, on ImageNet dataset. And with one single cloud TPU, which has 8 core, we could train the entire RasNet 50 model in under 9 hours. And the best part was the total cost was little under $39. And if we use a preemptible TPU, the cost was almost 1/3 to a little under $13. So in $13, you have a supercomputer at your disposal to train a very complex model. Isn't that incredible? And with version 3 and using many, many chips in parallel, in this case, 1024 chips in parallel, we could train RasNet 50 model on ImageNet dataset up to 76.3% accuracy in just 2.2 minutes. It's just mind-blowing to think that this machine could process 1 million images per second, more than 1 million. That's just amazing. You could train models in 2 minutes by the time you drink your coffee. So it will save you so much time. You can do so much more with your time, do something interesting instead of waiting for model to finish. So in order to help you get started quickly, Google provides many open source references for cloud TPUs. And with these open source references, you can solve many real life problems. For example, you can create image recognition algorithms, or you can create machine translation, or do speech recognition, or image generation, or many, many different things. All you have to do is bring your data, use the existing model to train them, and you're on a great start. But if you choose to decide to work on a special problem, you can always write something from scratch using the libraries that are made available. And we support many, many different frameworks, so you can get started with all the tutorials and knowledge that is built in the community about TensorFlows, Keras, and many, many different frameworks. So now let's hear from BCG Digital about their experience and their journey of building AIML algorithms and models on the top of Kubernetes. Mahadevan.
Thanks, Maulin. So in this portion of the presentation, we'll actually go over our team's experience with using GKE. In particular, we will share some of the best practices that we followed so that we can actually leverage all the resources we commission, and it's actually simple, fast, and cost-effective. So just to give a scale of the type of problems that we as a larger GE face, in every 2 seconds, a plane with a GE engine takes off somewhere in the world. Nearly 30% of the world's electricity is actually made by a GE turbine. Coming more closer to home, we are Baker Hughes. We are an oil and gas company. So this is the world's first full stream company which actually takes care of exploring oil, extracting oil, transporting, and refining all the way through the entire life cycle of oil. So in order to sort of manage all these assets properly, we have to deal with a lot of models. We're talking of thousands of models. For us, a model is something which links inputs to its outputs. So how do you sort of build these models? So in this case, we leverage the same framework that Maulin mentioned, where we use GKE, that is sitting on top of the hardware layer, and we utilize the framework that we kind of started off at Baker Hughes called the Depend on Docker. So this helps an analytics engineer to package their analytics into containers. So it gives a sequence of scripts and a process that can help institutionalize how analytics could be built, run, tested, and deployed. So all the analytics would be actually packaged as containers, and that would actually feed the applications that you see at the top. So the applications would range from data management. We deal with a lot of data, which we'll talk about soon. Also, a lot of other applications where we deal with anomaly detection, just to find if a system is operating normal or abnormal, is it time to shut it down or do some preventative action over it. There are lots of other concepts of applications where we deal with the amount of remaining useful life that a part has, and definitely optimizing the operation. In order to do this, we need to have all these applications. And now let us look at what is a cost of a false prediction. A false prediction in our case can actually mean we need to shut down a plant. Or probably we need to sort of tell a plane cannot take off and it will be stuck at the tarmac. The results are pretty cost sensitive, and we are going to actually lose a lot of money in the process. Therefore, we strive a lot to actually get very accurate models. So how do you build accurate models? We do have to build, say, a model for a small asset. We are looking at around 5 or 6 engineers who would spend around a month or 2 to make a model that is pretty accurate. Now, if I were to scale it for an entire plant or a refinery, I'm talking about thousands of models. No way this model can be scaled, or this traditional way of bringing in more people and trying to sort of like build models cannot scale. And on the other flip side, it is not as simple as commissioning more nodes and clicking a button and say go for the models to be created. So we need to do something different and proper to sort of leverage all the machines that we commission. So what we will highlight in the subsequent presentations are the things, or the bottlenecks that are there in the process, and how we overcame that so that we'll be able to build these models at scale while still being cost effective. So let us focus on the first example where we look at the data wrangling exercise. So we deal with a lot of data here. So if we take a simple refinery, we are looking at around 3,000 sensors or so that is generating data. The sensors can be generating data at different rates. It can be in seconds, some can be in minutes, few seconds, etc. So all these data has to be connected. And therefore, for the 3,000 sensors, over a 2-year period, we are talking about trillion rows of data. This is pure raw data. And this raw data needs to be sort of converted into some workable data that can be fed into the analytic, correct? And so you can also expect different analytics would need the data at different rates. So you need to prepare different sets of data to feed different analytics. And moreover, all the raw data that we get would not be really clean. It has to be cleaned for some missing data because somebody forgot to turn on the switch to record the data, or some wire got tripped over time. So we need to go and clean up the data, fill in the missing data so that it can be prepared in a form that it can be used by the downstream analytics. So the working data set that we deal with can be of the order of 1.8 trillion rows. And therefore, that is a lot of data to deal with. So how do we sort of handle it at scale? So let us look at the case of the graph that I have shown here to explain the concept. So there are two axes in the graph. The vertical axis is called the capability axis. It's actually telling how fast of a processor you have, how good of a CPU you have. So the further north or further up I go along the axis, I'm sort of going towards a supercomputer realm, and I'm sort of like saturating the processor. What is on the horizontal axis is called the capacity machine, where we actually can increase our capacity or capacity by scaling out the machines and commissioning more resources and using them. In the case of data wrangling, we are going to process it typically at a tag-wise level, meaning each tag can be taken, it can be filled in for missing data or resampled to go and get its answer. Or we can deal with a group of tags, because there are some things that physics governs. For example, a heat exchanger, the temperature sensor in it, is going to be in sync with the ambient temperature that's being measured outside. I cannot treat them as independent. So we are going to deal with sensors by itself, or a group of sensors that we would know a priori based on the physics. In either case, this process is pretty well optimized. That's why to process a single tag or a per tag cost, which I've indicated by the circle over there, is almost further north in the vertical axis, and I've indicated by the circle over there. Next, if I were to sort of get a certain target performance, where we say we want to finish this particular inline operation in a few hours, that positions where our target performance for n tags has to go. In order to do that, we can come up with how many machines we have to scale out to achieve the performance. Later on, Murali would actually show a demo of how we were able to achieve scale up with different nodes, and he will specify the cost and the speed trade-offs over there. Next, we'll actually focus on the deep learning example. Any deep learning model will actually go through a process of an architectural search so that we can actually get the best model. We are striving till the last mile to get an accurate model, because the cost of a false prediction is pretty steep for the industrial case. How is it typically done? A subject matter expert would take and sample different regions. He would decide based on how the model is moving around, how we could tune the number of layers, what kind of a dropout we need to use, and other activation parameters. So in the case of BHG, in order, if you're going to build like thousands of models, we have automated this process, where we start off with a sample space that is indicated by the red crosses that you see over there. We train the deep learning models in those space, and we take the results, and we actually are going to look at certain outcomes from those models, with which we actually use to fit a model, with those being the outputs and the inputs being those red crosses. That's a meta model that we built, which can be very quickly queried for other architectures that are derived from that. We go and search the space of the meta model, which is a surrogate model, and come up with the blue set of dots, which is actually the Pareto front that indicates the best choices for the next path of runs. So from that blue curve, we can pick a couple of dots and relearn the process, couple it along with the original red X's to refine the model, and keep on continuing the process. So as you can see, this process is an iterative process. You start off with the red X's, you come up with your best candidates which are sitting in your blue curve. You then again refine the model, you go again to the red curve, and you keep on pushing the process till the end, till the point where you're sort of happy, or you have enough trade-off to the cost versus the amount of effort you're going to put in. So in this case, what you see here, we looked at a deep learning model which had around 10 plus architecture parameters that we had to tune. We actually searched over 250,000 architectures. And the proof of the pudding is actually in the result we get. So the final answer that we got out of this process, we actually had a 10x improvement in the training effectiveness over a model that was done by a random search by a subject matter expert. So next, we'll sort of look at how we dealt with some of the process bottlenecks and how we sort of like removed them to get the full speed that we really need to achieve. So first, we'll start looking at the containers. As we said, we build a lot of containers, and that's the box that we show over there. And our containers are encapsulating different analytics. So it can be with different complexities. So some containers might need GPUs, might utilize them only for a small level, say 20%, 30%. Others might saturate it completely. So So therefore, we need, or the containers can actually have much bigger footprint. So if I were to restart the container every time I'm going to make a run, I'm going to incur a big startup time for the container. If that is a bottleneck in your building process, we could overcome that by starting the container as a service, where we can actually run an infinite loop to maintain the container active. We can exec into the container and sort of run the process and get the answer back. So that's how we can overcome situations where the containers actually have a much larger startup time. The second, we need to move data into the container and outside the container to build models. Typically, the training data is pretty big. So we don't want to copy information into the container. So the way in which we do it is we map drives. So we avoid copying huge files into the container and bringing it out. And all the input and output that, as I said before, are pretty well structured. So the output we deal with are the outcomes that we want from the model. Those are all exposed as JSON files that we'll be able to track and move it down. So that's how we handle the data. And finally, more importantly, as I said, each container is not going to be using all the resources to its fullest potential. I should not assign this container to run on this particular GPU. So what we do here in this case is we actually run a max case of the container so that we can determine how much GPU it utilizes and how much memory it utilizes. Knowing that, we'll be able to use the fact and schedule multiple containers to actually run on the same GPU so that we'll be able to max out the GPU that we commission. So if you sort of look at the graph, I've just intentionally shown the blue dot to be on the lower left, just to indicate conceptually that this analytic does not use the GPU all by itself fully. So how do we sort of go up further north and to the east? We can actually use the fractional resource utilization to go up north and use more number of GPUs to go further towards the right and go towards the start. So that is how we'll be able to achieve the best performance with all the resources that we commission. Next, we will look at the aspect of orchestrating containers. So the entire process was pretty iterative, as I said. And so the way in which it starts is we have a node which will decide what are the next iterations I need to spawn. So it spawns the next set of iterations, after which it actually has to collate the results and decide if I have to continue with the next set of iterations, right? And those intermediate levels are actually made stateful so that I can make a decision whether I need to continue further or not. And one of the things that we noticed was there's a limitation of a for loop inside the Kubeflow. So we had to actually unravel it, and we made it in a form where we spawn, we accumulate. We again spawn, we accumulate the process to continue it and get the results. So in order to sort of reach the full potential of all the resources we commission, we had to use this fractional GPU allocation so that we can get a near linear scale up for the resources that we have. I will quickly show the results at the end after Murali finishes his part. Thanks.
Yeah, thanks, Mahadevan. Sorry. As Mahadevan said, we are in oil and gas industry, and we are not a digital native industry. There is a vast difference between a digital native industry and an oil and gas industry. Usually, the data we get from digital native industry is rich, and it is almost ready to be consumable. But in oil and gas industry, we collect the data over last 30 years, and it can be very messy. And very often, we don't even know what we are looking for, okay? So unless we explore. So the exploration stage of the data itself is quite different from the digital native industries. And it is highly iterative, and we have to iterate so many times, till the data scientists come back and say that, yes, now the data is consumable. So, I mean, some of you may be like me, maybe from a traditional data background, and scale up was the solution, but now we have scale out, and the Kubernetes really comes as a great rescuer here. Okay, so here I would like to show. So for the last couple of years or more than that, we have been a very heavy Kubernetes shop, and we use Kubernetes extensively, both on-prem and on various cloud platforms, and we have a heterogeneous environment. So we have been managing these Kubernetes clusters on-prem, and some of the challenges. Some of you know that the patch management is the biggest hassle, and we need to take downtime, and we need to go back to the data scientists, and Mahadevan will be very frustrated that we bring the clusters down in the middle of a big exploration, model development. And the two other hazards what we have seen so far is the auto-scaling. Auto-scaling is not available. I mean, it's not so easy to implement it on-prem, and then the cost. Okay, it's not cost-effective. If we are fixed with 100 nodes, you have to continue to consume all the 100 nodes. Then we started recently migrating to GCP, and we have been using GKE. Here, the biggest advantage, as you can see on the dashboard here, this has been made possible because we used Stackdriver and GCP. So we collect the metrics at a granular level, and this is in fact a cluster of clusters. And we can immediately see which node is coming up or which node is being shut down, is being spun down, and so we can continuously monitor it, okay? This is made possible only because we run it on GCP. The other aspect is the management of the cluster. Okay, now we don't have to worry. We have a small DevOps team, and they are now relieved, and Mahadevan can spend more time on his model development rather than maintaining the clusters. The third aspect is cost. Okay, because we provision them only when it's needed, we don't spend as much money as we used to do before. I'll have a simple demo here. Before we go to the demo, let me explain here. So we took a simple query, one of the simplest of simple queries as soon as we receive the data. That's about 55 billion rows. And when we ran it with 10 nodes, it was costing typically like $1, okay? And when we scaled it up to 40 nodes, we finished the job in 130 seconds as against 700 seconds, and the cost came down by 28%. So this is where we become a differentiator, because we finish the job in far less time, and we achieve it at far less cost as well, okay? So this is I hope the demo gods will help me. Right. So this, as you can see, this is a cluster of 40 nodes. Okay. And this is the running average, one of the simplest of simple queries that we do as soon as we receive the raw data from the customers. Okay. So we can see the progress of the query. It's against 40 nodes. Sorry, yeah, I just refreshed it, and let me forward it in the interest of time. So as you can see here, it's 55 billion rows. 55 billion rows, we could complete it in 2 minutes and 9 seconds, and the cost of the query is less than $1. Okay, that's what we achieve. And this is against 55 billion rows, and as Mahadevan said, typically for a well or for a simple equipment, what we take, when we expand the data, it goes to 1.8 trillion records. So we experiment this with the less number of nodes, and then as the need arises, we scale up, and that's how we achieve at a cheaper rate. Okay. Thanks, Mahadevan.
Okay. So I'll quickly summarize the results from the auto-scaling experiment that we did. So where we actually look at the graph over here, where we are trying to increase the number of GPUs, and we can sort of see whether we are able to leverage and utilize it completely at all. So look at the bottom two graphs. So what you see on the right side is the number of GPU nodes, where we are doing an experiment where we are able to actually increase, or in a preset manner, the number of GPU goes from 1 to 2 to 3 all the way till 8. And what you see on the left side, the lower left, is actually telling how we are able to utilize the GPU. So we start off with 1 GPU beginning, and then we ramp it from 1 to 2. You can immediately see the percentage utilization drops to 50, and it again kicks up and almost goes up instantaneously to 100%. The next step, when I go from 2 to 3, you can sort of see it docking down and again goes up to 100%. So the main takeaway from here is the way in which we did the fractional utilization and we are able to assign it to the GPUs. We are able to nearly assign full utilization as we increase the number of GPUs, and more importantly, as we take the GPUs away, we're also able to ramp it down. So this one just summarizes how we're able to show auto-scaling works when we ramp up and ramp down the GPUs. The next case is how we actually make it work on the GKE. So in this experiment, what we did was we had a 32-node cluster, and instead of actually allowing the cluster to operate or go up to 100%, we preset the limit that it reaches, so to 80%. So once we load up the machine, as we sort of shown by the experiment 1, and because we are capping it off at 80%, the number of node requirement actually jumps instantaneously from 32 to all the way to 40. It's pretty much flat, and once the load tapers down, it releases the GPUs and comes back again. Just to see the repeatability, we again fired the process again. So that is the experiment 2, where we fired the same process with the same constraints. 80% as your threshold, and as you can see, the GPU nodes which got commissioned automatically actually increased to 40, and then it came down. For the third experiment, what we did was we wanted to simulate a case where we partially permit an increase, and then due to some other case, we're actually taking the GPUs away from the system too. So we capped it off initially to some intermediate number, and then slowly started removing the GPUs from the system to see how it responds. As you can see, it got capped over there, and we sort of like brought down the GPUs in a preset sequence in the bottom right. As you can see at the top, the time it took to sort of complete the entire process actually expanded along the horizontal. So again, in order to maintain a high GPU utilization, we need to have a good way of orchestrating, and you need to design the underlying containers to respect that, and so that you'll be able to leverage it fully. So in summary, if I were to summarize the best practices, the cloud scalability actually requires a lot of planning on how you build the containers, how you understand how much resources it needs, and manage it. And definitely look for a lot of redesign and iterative steps that needs to happen. And finally, for load balancing, the fractional GPU utilization and other things has to be adhered to so that you can use the resources fully.
Thanks, Mahadevan. I'd like to say a couple of things here. Scaling up is not panacea. I mean, it can be, sometimes it will end up as a brute force, and it is highly iterative. A lot of patience and planning is required. And load balancing is another aspect. You got to think about it very carefully. And adaptive space. Be prepared to have some space so that you can redesign your architecture and take a different route, a totally different route than from where you started. It's not easy. I mean, now that you have Kubernetes, particularly on GKE, it's made much more simpler. Now, for example, scaling up is much more simpler right now. For example, typically scaling up about 200 nodes, it happens in less than a minute. So, so you got to have a lot of space to adapt to the changes, but you can do many things with Kubernetes. Yeah, thanks.
Thank you, Thank you, Mahadevan and Murali, for sharing your insightful experiences with us today. So let's summarize the key takeaways. So at Google, our mission is very simple. We want to empower your team to drive innovation by making AIML simple, fast, and cost-effective. We are making AIML simple by offering data scientists their friendly notebooks. We are freeing them up from managing the infrastructure and also providing higher level abstractions like TensorFlow jobs and TensorFlow servings so that their work becomes super simple. We are making AIML fast by offering you on-demand scale up and scale down, and also hardware accelerators like GPUs and TPUs. And we are making AIML cost effective by making your teams more productive with advanced tooling, avoiding the vendor locking with open platforms like Kubernetes and Kubeflow and many other things we have developed in Google are available in open source environment. This way you can write once and run anywhere. And finally, but most important, you have preemptible GPUs and TPUs to further lower the cost for your batch workloads.